Gui Chang Chen. I tried today to learn the because it is not written in this way, but I tried to learn. I hope that. Okay. Well, this one. I need this one. So this is the plan of my talk. The first part, just an introduction of the equations. The equations are very, very long and obtained under some assumptions. So it is the only place where I think to show you the equations. Then in the second part, I would like to talk a little bit about hyperbolic problems, hyperbolic systems, and in particular boundary value problems for hyperbolic systems in general. And in the end, something about shocks, strong discontinuities in MHD, classification in MHD. So start from here. The equations concern the motion, a macroscopic motion of an electrically conductive fluid and electromagnetic fields. Here we don't consider viscosity or magnetic diffusivity, so the system will be hyperbolic with no diffusion. The first equation is the continuity equation for the conservation of mass. Rho is the density and V is the velocity. Then we have the momentum equation for the conservation of momentum. And here on the right-hand side, we see J. J is the current density multiplied the vector product by H, the magnetic field. Now we take the Ampere's law written in this form. The last term is the displacement current. This E is the electric field and epsilon the electric constant. We assume that this can be neglected because it is very small. So we have only the J is given by the curl of H. We substitute here, J. We obtain this product, we develop it in this form, and in the end we get the equation that we will consider. Again, the momentum equation written in this form here. Then consider Faraday's law, okay, for H and E. Now we want to eliminate the electric field. We consider in Ohm's law relating J, the current density, V, H, and D. We assume formally that sigma is infinite. So this is zero, this part is zero. We obtain the electric field from here, substitute, and obtain this final form of the equation for the magnetic field. Moreover, we require that the magnetic field is solenoidal, so the divergence is zero. It is another equation that we have to add. And finally, the conservation of energy that now is written in this quite complete form. Again, as a conservation law, because we have derivatives of quantities. And here we have the time derivative of the total energy of the system. Small e is the internal energy. Okay. Then we take all together, and this is complete system, where mu 0 now is, for simplicity, is taken equal to 1. So again, continuity equation, the equation for the momentum, the equation for H, the energy conservation, plus the constraint on H. This is the complete system. It is a system of first order equations, as you can see. Okay. We can drop the last, from the system, the last equation, because this is a constraint that can be seen just as a restriction on the initial data. In fact, is at the initial time h is solenoidal. From here, we take the divergence of the system, and we get the time derivative of the divergence is 0. So this is 0 at the initial time, and then it is 0 for all times. Okay, so this last equation will be only a restriction on the initial data. And what else? Oh, so we don't consider the last one. We take only equations with evolution in time derivatives. This system is written in conservation form. We have derivatives of quantities everywhere. And we see that it is a system of 8 first-order equations with 9 unknowns. 8 because we have 2 scalar equations for ρ and E, the internal energy. 3 vector equation, 3 plus 3 for V and H. So we have 8 first-order equations, but we have 9 unknowns, because the unknowns are scalar unknowns, ρ, P, and E, and vector unknowns, V and H, so 3 plus 3 and plus 3, 9. So the system is not closed. But we can consider from thermodynamics the Gibbs relation, this one, where so P is the pressure, E is the internal energy that we have already seen, T the absolute temperature, S the entropy, and V the specific volume. Okay, we have this relation. We cannot see that P is this derivative, so can be written in terms of ρ and S, for example, and also T can be written in terms of ρ and S. So if we choose ρ and S as a thermodynamic independent variables, then P and E can be written as functions of these quantities. The form of the function depends on the constitutive law of the fluid. So we have only 2 independent variables now, ρ and S on the thermodynamic side, and in the end we have a closed system because we have 8 unknowns for 8 equations. And this is the equation, the system that we will consider. Okay, this is the conservation form of the system. But we can write it also, it is convenient to write it in another way. It depends on the kind of calculations we are doing, but it can be more useful to write it as a symmetric system, to take the derivatives of the functions. In particular, there are different ways to symmetrize the system. We can symmetrize using the pressure, but also using the total pressure. And the total pressure is this one, is the sum of the thermodynamic pressure plus this one, which is called magnetic pressure. In terms of this Q, and taking S as the other thermodynamic independent variable, so in terms of Q, V, H, and S, we can write the equation, the system before, in this strange form written here, where we can see, at least we hope to see, that all the coefficients of the derivatives are symmetric matrices. Here, for example, this is symmetric. We have terms on the diagonal and so on. This is symmetric, okay? It is symmetric. And the first coefficient, this matrix here in front of the time derivative, is also positive definite. So the system can be written in this way. All matrices are symmetric. The first one is also positive definite. So the system, in the terminology of SER of the last week, it is symmetric hyperbolic in the time direction. The time direction is special because the coefficient is also has a sign. It's this one. And the condition for the symmetric hyperbolicity are these two conditions here. So physical condition, the density has to be strictly positive, and the derivative of the density with respect with respect to the pressure, or vice versa, per ratio in terms of rho, has to be also strictly positive. Okay, so this is the form of the system that we consider from now on. Okay, now other things. So we know that in general the solutions of a hyperbolic quasi-linear system may develop singularities of the form of shock waves, or more general, there are also other kinds of strong discontinuities in finite time, independently of the regularity of the initial data. Okay. So now we consider this general system, hyperbolic system of conservation laws. The space dimension is D, so in RD. The system is n by n. So U, the solution takes values in Rn, n components. Fj, this function, nonlinear functions, are smooth from Rn to Rn. So here we have n unknowns and n equations. Okay, and now let's see what is a shock. Well, I consider a planar discontinuity at a point. I fix a point where I know there is a discontinuity. I take this plane, hyperplane, passing from the point in space-time variables. So it assumes that it has the form written here. So this sigma, we can see that it is a velocity from dimensional analysis, and it is the velocity of the front. So we have this parameter here, the velocity, and this nu here, which is a normal vector, constant. Okay, it divides the space into parts, this plane, and we denote by u plus and u minus the values of u in the fixed point from each side of this sigma. Now we take piecewise smooth solutions, which means solutions which are smooth in the two sides of the space obtained from the introduction of sigma. Along the discontinuity front, sigma, a solution, in order to be a weak solution of the system, a complete system, must satisfy the so-called Rankine-Hugoniot jump condition, which are this one here, from which we see that the square bracket denotes the jump. We see that the values of u on one side and on the other side, given nu, determine sigma, which can be computed from these equations. Okay, so we have more condition in order to, we have the differential equations in the two sides of on one side and the other on sigma, and this additional condition, jump condition on the front, in order to have a solution, a weak solution. Okay, now, so given you...
Let me ask you this question.
Yes.
If you have several variables, you will have conditions for other variables, right?
U is a vector, in fact. We have
Yeah.
several variables.
So this is a vector equation, but
Yes.
sigma is?
Scalar.
Okay. And will you get the same scalar all the time?
It should be the same. Yes. So
this
it is a
this
strict...
condition.
Oh, yes, in fact. Yes, it is. Yes, yes. Right.
Okay.
Okay.
Sorry.
So here we take the derivatives of the functions in U. So it is a Jacobian matrix, and I denote it by AJ. Here is given a vector nu. This is, if you think to a decomposition of the differential operator, we have the front, and we take the component of the differential operator in the normal direction, obtained characterized by the vector nu. So this is A of u mu is the quantity here from, this is a matrix, okay? We know that the system is hyperbolic, so this matrix has real eigenvalues, n real eigenvalues, that we denote by L1, Ln, which depends, of course, in general, by u and nu, and Rk, the corresponding right eigenvectors. So, this is the definition of a so-called Lax shock. U plus minus is a shock if there exists a family of eigenvectors, so characterized by the index k, so Lk, such that the gradient of Lk dot Rk is never 0, it is always different from 0, so Lk is genuinely nonlinear, in the terminology also of Serre the last week. And we have these strict inequalities. So in between we see the shock velocity. Oh. So the sigma is never equal to one eigenvalue, we can see from here. And the value is in between. If we take the same state u minus, it is between Lk minus 1 and Lk, or between Lk u plus, Lk plus 1 u plus. It is in between, so it is never coinciding with one of those. And also that if we consider Lk here, sigma is between the two values obtained by the eigenvalue of the same family. And we say that the characteristics in one family enter the shock from both sides. So we have something in one dimension. Here I have xt. This is the shock. And Lk is entering the shock in this direction on the one side and this way on the other side, like that. So there is one family of characteristics entering the shock from both sides. While for the other characteristic, the other families do not cross the shock. So this is the shock. So here we see that we have strictly inequalities. So we expect that these are stable patterns with respect to small perturbations. And also, well, sigma is always different from the eigenvalues. So the coefficient, this matrix coefficient or the normal derivative A of u nu has eigenvalues always different from sigma. Sigma is determines the plane of discontinuity. So what happens is that this matrix is non-singular here. It's always invertible because the eigenvalues are different from sigma. And sigma characterizes the plane. And so we say that this interface, the front sigma, is non-characteristic because of that. So this is a condition of regularity of solution in the sense that this allows to get the normal regularity, normal with respect to sigma. Other definition, this one, we have a content discontinuity if again there exists k such that the corresponding eigenvalue is linearly degenerate, which means this one, this fact here. So we had always different from 0 before, now it is identically 0, the scalar product. And we have the eigenvalue coincide with sigma on one side or on the other side. So in this case, we have this is the discontinuity. Maybe we can have this one. maybe, okay, and then this is parallel. Here, take conside. Something like that. So this is a characteristic interface because this coefficient, the coefficient here is not invertible, is singular at sigma, because one of the eigenvalue coincides with sigma. Okay, what do we expect? Because of the fact that the interface is characteristic, here we expect a loss of regularity in the normal direction, because usually we have, so for example, with some boundary condition, we have a problem of this form. When we look for a priori estimate, first, usually one takes the tangential derivatives that satisfy a boundary condition of the same form and get an a priori estimate for the tangential derivative. And then try to get an estimate for the normal derivative. So if I decompose and I put in evidence that coefficient, the nu is the normal derivative plus okay, tangential things. From the equation, if I have already estimated the tangential derivative, I have this one, this part, this is given, and I obtain the normal derivative from the equation. So if the coefficient is invertible, I get the derivatives, otherwise, no. Or maybe only some components. Okay. And typically one expects to control one normal derivative using two tangential derivatives. So there is a loss of regularity in the normal direction. Okay, now, so our problem is this one. We are looking for a piecewise smooth solution with two possible states, u plus and u minus, on one side or the other of a front. Okay, so we assume that we have sigma of t described in this way. It is an hypersurface. Assume that it is given in this form. So there is the last space variable, xd, is given by a function of time and x prime, the other space variables. So assume that this sigma of t is a graph of a function written in this way. It divides the space in two parts, above and below. We consider the differential equation above and below with the solution u plus u minus. We want to solve the equation written in this form. We have transmission conditions of the Rankine-Hugoniot conditions here on the front. We add some initial condition, and this could be our problem in general. Well, these n, 0, and 1, and d are the components of a vector n depending on time, a vector orthogonal to sigma of t. This continuity front, sigma of t, is described by this unknown function phi, which is an unknown of the problem. So this is a free boundary problem. This is the only place maybe where I say the words free boundary. But before. Okay. Now, we simplify a little bit the problem in this sense, because we assume that the initial datum is piecewise smooth, okay? This continues along the given smooth surface sigma of 0, so the initial form of this smooth hyper, no, it is not a curve, it is a hyperplane. But now we add this restriction. In order to be to ensure that only one nonlinear wave will issue from the initial curve of discontinuity. The initial data are restricted by imposing strong compatibility conditions. It means that in general, if we have initial data with the discontinuity, we can expect that for positive time from the discontinuity, there will issue wave patterns of different kinds, shocks, rarefaction waves, contact discontinuities, all together. And here we want that there will be only one nonlinear wave, only one. One shock or one contact discontinuity, only one. And this is obtained if the initial data satisfies some very strong conditions that avoid the income or the other kind of discontinuity. So only one. So the problem is find good compatibility conditions on the data such that there will be only one wave of the required form, only one. And then try to solve the system, at least to solve the problem, at least for small times. Okay, so we try to understand how one can work for this kind of problems. Now we linearize everything. Try to get some information about this problem. We linearize about a constant, piecewise constant solution with a flat front of this continuity, and assume that we can, after some transformation, we can go to this linearized system. So here we have a system with constant coefficient, for example, written hyperbolic system, in a half space, so xt positive for positive times. We have some boundary conditions in homogeneous form obtained from the linearization of the Rankine-Hugoniot conditions. Some initial data here. Okay, so we assume that this is an hyperbolic operator with eigenvalues of constant multiplicity. N is the size of the system, Aj are constant matrices. We assume also that the front, so the boundary is xd equals 0 is non-characteristic, which means that Ad, the normal, the boundary matrix is invertible, so the determinant is different from 0. We also assume that the rank of M is the boundary, the matrix which describes the boundary conditions. This matrix is P by N, and P is precisely the rank of this matrix, and it is equal to the number of the positive eigenvalues of Ad, which is a necessary condition for well-posedness of the problem. Okay. Now, I want to introduce the Kreisler-Lopatinsky condition, which is important for initial boundary value problems. So in order to study the relation between the system of equations, differential equations, and the boundary conditions, that relation. So first I want to do it in a very naive way, and then in a more rigorous way, but just to explain how it works. So first we see that we have a system here, homogeneous of equations. There is a scaling property, this one. So the problem is invariant under this rescaling. X goes in Cx and t in Ct for any C, any number C. Okay, this implies that the existence of a solution bounded in space which grows in time implies the existence of a spatially bounded solution, again, that grow arbitrarily quickly in time because of this scaling.
Why arbitrarily quickly?
Because I have one solution, see, which grows in time. Then I can construct another one where instead of t there is ct using the rescaling, and cx instead of x. Cx, okay, is okay because it gives the x part is bounded in space, so it is still a bounded function in x, but in times it grows like c times t, and c is arbitrary, so it grows arbitrarily fast. It is still bounded in space and grows in time.
Exponentially.
In fact, it grows exponentially. So the result of this property is that there is a sharp division between weakly or strongly stable problems without growing modes in time, and violently unstable problems with growing modes. Now I show you. Okay. A sufficient condition for the strong L2 well-posedness of the initial boundary value problem is provided by the so-called uniform Kreis-Lopatinsky condition, UKL, or uniform Lopatinsky condition for short. Now I explain a little bit. So to obtain this condition, we look for Fourier solutions of the boundary value problem of the differential equation plus boundary conditions without initial condition. We extend time from minus infinity to plus infinity. So Fourier solutions that oscillate tangent to the boundary decay away from it, from the boundary, of this form. So here there is an exponential with I multiply the unit, imaginary unit. This, the space variable from 1 to d minus 1 in this form, these coefficients, and here also minus I omega t, okay? Something oscillating along the boundary, so depending on x1, xd minus 1, depending on time, oscillating in time again, and the xd dependence is given here, and we ask that this solution decay away from the boundary, so as xd goes to plus infinity, this goes to 0. This omega will be in C, okay? So typically we observe that u decays exponentially in space and is given by sum of terms of this form here with this exponential here, and in order to have the decaying property, the real part of beta j, the coefficient, has to be strictly positive. So we obtain typically these kind of things. Now, there are three alternatives essentially that correspond in a very rough way to growth oscillations or decay in time of these appropriate Fourier solutions. First case, if the imaginary part of omega is strictly positive and the real part of beta j is positive. So this is true for every j. We have a solution that grows in time because the coefficient of t, the real part is this one, which is strictly positive, and it decays, so it grows in time and decays in space because of the condition on the beta j. Okay. So in this case, using the scaling property I said before, we have spatially bounded solutions that grow arbitrarily quickly in time. We can construct them using the scaling, and this gives a problem which is subject to this Hadamard instability, and it is imposed in any Sobel space. We say that it is violently unstable. Second case, this one, the imaginary part of omega is 0. Here we have the real part of beta j is non-negative. So this solution oscillates in time and does not grow in space away from the boundary. And this solution is a limit of solution of the first type. first case. Okay. Then we say that the problem is weakly stable in L2. Well, and in general, the problem is well posed, okay, but we observe a loss of derivatives in the energy estimate. Example, Rayleigh surface waves in elasticity or contact discontinuity in MHD. Third case, there are no such solutions of the PDE and boundary conditions, growing or oscillating time, and we say that the problem is strongly stable, and we have good L2 energy estimate without loss of regularity. Okay, and this is the case of the uniform Lopatinsky condition. Now, second part, I would like to make everything more precise. I don't want to bore you with too many details, but just to give you an idea of the kind of analysis. So again, this is our problem as before. Now we consider this is our solution. It is a solution of the problem with homogeneous equations. We take the Fourier Laplace transform, Laplace in time, so in t, and the dual variable is denoted by tau, and Fourier in x with dual variable is denoted by eta, Fourier with respect to x prime, so not with respect to xd, which is the normal space variable. We take, okay, the transform, and we reduce the problem to this ODE system of equations. This symbol here is this one that is obtained from the equation with, okay, this is the ODE problem in xd. This is the boundary condition with xd equal to 0. Okay, we consider the stable subspace corresponding to the eigenvalues of the symbol A with the real part negative. This is the stable subspace. So the Kreis-Lopatinsky condition in simple form is this one. If we take vectors which are in the stable subspace, so they are decreasing at infinity and in xd, and satisfy homogeneous boundary condition, then the solution is 0. It must be 0. For all tau with real part strictly positive. So this is Kreis-Lopatinsky. In an alternative way, there exists a constant which may depend on eta and tau, positive constant, which gives this estimate. So you see that if V it is in the stable subspace and satisfies a homogeneous boundary condition, MV is 0, so AD of V is 0, AD is invertible, and V is 0. And we are in this situation here. Okay, this is the Kreis-Lopatinsky. The uniform Kreis-Lopatinsky is this one. We have the constant is the same estimate as before, but the constant is independent on eta and tau. So it is good for all states, all frequencies. This is the difference. And a good tool for the analysis is the so-called Lopatinsky determinant. Here we take a basis, orthogonal basis of the stable subspace, x1, xp. P is the number of boundary conditions. Okay, well, I skip this part. Okay, I define the Lopatinsky determinant. So we apply M to the vectors, the P vectors of the basis. We compute the determinant of this matrix. This is the Lopatinsky determinant. And we see that the Kreis-Lopatinsky condition is this one. The determinant is always different from 0 for all tau with the real part strictly positive. While UKL, the uniform form of the condition, is that this is again, always true, but for all tau, even with the real part vanishing. So, okay. It is a stricter form. Now, what happens? So, first consider the non-characteristic case, where the situation is better, because we have these results. If Kreisler-Plotkinski is not satisfied, then the problem is ill-posed. So for the well-posedness, Kreisler-Plotkinski is a necessary condition. If we have the uniform Kreisler-Plotkinski condition, then this is equivalent to the L2 strong well-posedness with no loss of derivatives. Okay. If we are in between, we have KL but not UKL, then we have a weak well-posedness of the problem, but the energy estimate may have some loss of regularities or of derivatives. Okay, this is for the non-characteristic boundary case, the picture is complete. For the case of a characteristic boundary, we have the same thing, that Kreisler-Plotkinski is a necessary condition for well-posedness, but we don't have the equivalence of the second point here. For the L2 strong well-posedness, we have to add some structural conditions on the differential operators. Okay, I don't want to go. I have time, but or maybe I can show some structural assumption. Only 2 slides. The general theory for characteristic problems is maybe found in a paper by Maida and Doscher, an old paper. It concerns the case of a symmetric hyperbolic operator with variable coefficients also, not only constant. The boundary is not simply characteristic, but uniformly characteristic, which means that the rank of the boundary matrix, which was A of U nu before, this rank is constant in a neighborhood of the boundary. So for example, it is not true for the Euler equations, for MHD equations, many physical problems, it is not true. But for the Maxwell equation, for example, this is true. Okay, we have these assumptions. We must have the uniform Lopatinsky condition. Some structural assumptions, like this one, for example. We have this decomposition of A of mu, and this part here has only simple eigenvalues. It is necessary to write it in this form. This is true for in some cases, but not always. For example, it is not true in 3D isotropic elasticity. An improvement may be found in the book by Benzoni, Sylvie Benzoni-Gavage and Denisser. Again, we have a symmetric hyperbolic operator with, in this case, with constant coefficients. M is also constant. The boundary is still uniformly. No, it is, of course, it is a uniformly characteristic boundary because the coefficients are constant, so everything is the same in all the space. They add this reflexivity condition here. UKL must be satisfied, always. And they take precisely the case where Maida-Osher is not satisfied because they take the case of the 0 here. And they can prove the equivalence with L2 strong well-posedness. And this is the case of Maxwell equations, linearized acoustics. Okay. Now, I pass to the third part, to the MHD equations. So we have seen that we have the Rankine-Hugoniot conditions that must be satisfied by piecewise smooth solutions. In the three-dimensional case, so I have a front in space described by this plane, sigma of t, which is again the graph of a function, phi. The Rankine-Gonio conditions are this system, so it is very complicated, of course. These conditions here are written with this n, which is a normal vector. N appears here, so Vn, Hn are the normal component of V and H. V tau, H tau are the tangential components. And also you observe that the first condition is a continuity condition for the mass flux, J, described in this way. Okay, this is important for our classification, this J, because, okay, these are the Rankine-Gonio conditions in general, but they are satisfied in a special form depending on the kind of discontinuity we are looking for. So this is the classification of strong discontinuities according to Jeffrey Tagnuti. First case where there is, you saw that J is continuous across the front. Well, we have MHD shocks if J is different from 0, so it is continuous, but there is a mass flux across the front, and there is a jump of the density. These are shocks. Second case, we still have J plus minus different from 0, but we have no jump in the density. These are the so-called Alphen shocks, or Alphen or rotational discontinuities. I discuss a little bit more later the different kinds, just for classification here. Contact discontinuity where J is 0, so there is no mass transfer across the front, and the normal component of H which is continuous. I show you again. You see that the normal component has to be continuous. It comes from the fact that H is solenoid. Okay, so Hn is continuous, but Hn plus and minus are different from 0. And the last case, which are the current vortex sheets, or so-called tangential discontinuities, according to this terminology, where still J plus minus is 0, and this normal component is 0. So there are 4 cases, J different from 0 here, and the jump or no jump in density, and J equal to 0, and Hn 0 or dot. This is the classification. 4 kinds. Okay, for shocks. For shocks, as I said before, the shock front is non-characteristic interface, so we expect that there will be no loss of derivatives of regularity in the normal direction, which means that we can use the standard Sobolev spaces, because we expect to have a full regularity of the solution due to this fact. Okay, there is another distinction between the kinds of shocks, but I don't go into details, slow and fast shock waves. Okay, so we have a general theory for shocks, also for general system, which gives the existence of local in time and the stability of initial boundary value problems with one single uniformly stable shock, which goes back to Blachin, but maybe more in more general form to Maida. That unfortunately doesn't cover the MHD case, but there is also an extension of the Maida general theory to a class of hyperbolic symmetrizable system with eigenvalues of variable multiplicity. And this is the case of MHD. And this extension is due to
What does
MTV
this
and
mean,
Zoom.
variable
Eh?
What does this mean? Variable multiplicity?
Big,
The multiplicity
it depends on the, yes, they
The
change
state.
on the state, it
Ah,
changes,
ah.
yes, on the state. Usually eigenvectors are constant multiplicity,
Yeah, right. I see.
yes.
So MHD.
But in case of MHD, they, with the direction of the
Direction.
state with the in different frequency, the different frequency vectors. Okay, so for shocks it is okay. The theory, the general theory is okay, and one can have the local existence of a solution. Second case here, Alphen shocks, where the Rankine-Hugoniot conditions are satisfied in this form. So we have a continuity of the pressure, continuity of the entropy, which means continuity also of the density, because of the constitutive law. This is the second equation that I wrote before. Hn is continuous across the front. We have this the continuity of this quantity. It is the difference between the velocity of the fluid and the Alphen velocities. The difference is continuous. Okay, J, the flux is defined in this way, can be computed, and it is precisely this quantity. So rho is continuous and Hn is continuous, and they are different from zero. Yes, because J is different from zero by assumption. And so rho plus is different from zero, Hn is different from zero, even if rho is continuous across the front. Okay, but the interesting point is here. Okay, we can drop the square. It says that we have the normal component of H is continuous. The modulus of H is also continuous, but H can change direction because the front. So it has one direction on one side and another one with this direction on the other side, even if the normal component is the same. For this reason, they are called also rotational discontinuity. So there is a jump of direction of H across the front. As far as I know, very little is known for this problem. So again, the front is characteristic. And it is known that for the constant coefficient case, so the constant coefficient linearized equations, which means planar Alphen discontinuities, they are never uniformly stable. So the UKL condition is always violated, never satisfied. So they can be weakly stable or violently unstable, but I don't know if it is, if there is a description of the two regions or of a weak stability, and violent instability on the other side. I don't know. And this was proved by Sirovansky for the incompressible case and Ilin and Trakinin for the compressible case.
This for linear
Linear constant coefficients. Okay. Constant discontinuities where J, the mass flux, is 0 and Hn is different from 0. The Rankine-Hugoniot conditions are satisfied in this form. So there is continuity of the velocity, continuity of H, continuity of the pressure, but if you think that the pressure is a function of rho and S, P can be continuous even with a jump of rho and S. If they are discontinuous in a right form, we have that rho has a jump, and we speak of density waves propagating along this front, or a jump of S. So another possible name is this one, entropy waves. Again, the front is a characteristic, and as before, for Alphen shocks, planar contact discontinuities are never uniformly stable. So they are either weakly stable or violently unstable. Again, I don't know if there is a precise description that says where, for which states we have UKL. No, we have weak stability or instability. I don't know. But there is this recent result by Morando, Trachinin, Trebesky about the well-posedness of 2D planar contact discontinuity under this stability condition, this Rayleigh-Taylor sign condition, which says that we take the normal derivative of the pressure, the standard pressure, not the magnetic pressure, standard, the thermodynamic pressure. The jump of this normal derivative has to be strictly negative. Okay, so it is similar to the Rayleigh-Taylor sign condition for the one-phase problem considered, for example, by Scholler last week.
This is two-phase problem, right?
Yes, yes. This is on the
Oh, I
jump.
see. So you're giving,
It is on the jump.
first giving normal direction.
Mhm.
Oh, I see. Then you
Consider
Fine.
you
It's
take
found
the
there.
normal derivative on one side, the other one,
Z direction.
you take the jump.
Yeah.
It is planar, this is a planar contact discontinuity. So we freeze the coefficients,
Yeah.
and also the derivatives are freezed.
Okay.
So we can take derivatives. So it is not, P is a constant with a constant derivative.
With constant.
No, you,
With
they
A.
take you take the system with the variable coefficients,
Yes.
and you freeze everything, so every coefficient.
Yeah.
So the functions and their derivatives. In this sense,
So P should not piecewise constant. Because you take derivative on direction.
yes, they are.
If piecewise constant, take derivative 0.
So yes, in fact, if you freeze the state, the derivatives are 0. But if you take the variable
Variable
coefficient problem and you freeze everything,
Mhm.
you freeze also the derivatives of the states.
I see.
So constant states with the freeze the derivatives. It's a strange thing.
So what is the background? So I see. Okay.
So you see, if there is no general description of the region of weak stability, you look for some sufficient condition, sufficient stability condition, which gives the weak well-posedness. Even if probably, in principle, the weak well-posedness could be obtained in a larger region.
It's a little difficult to understand this condition. One phase problem is, you will go.
For example, you
have
take
to
the
fix
problem
different-
with variable coefficients, and you fixed the coefficient only in every point of the
Yes,
front,
Yes.
in every point.
And this direction. I see.
This is considered as a first step. Then they should try to extend it to variable coefficient case, and that to the nonlinear problem. Okay, and current vortex sheets. The Rankine-Hugoniot conditions are satisfied this way. So this is the velocity of the front is the normal component of the velocity. The total pressure is continuous. Hn is 0. Okay, we may have a jump in the tangential velocity, which gives a concentration of vorticity along the front. We can have a jump of the tangential component of H, which gives a current concentration on the front, and also possibly jumps in density and entropy. Here there are more results. Okay, again, the planar current vortex sheets are never uniformly stable. As before, the front is characteristic. Under this stability condition that says that on the two sides of the front, the magnetic field, the two magnetic fields are not parallel, and the smallness condition on B tau, on the jump. Trakinin first studied and obtained the stability of the linearized equations using a different symmetrization of the system of equations, and proved an a priori estimate by the energy method with the loss of derivatives. But then also the existence of the nonlinear 3D current vortex sheets was shown by Kui-Chan Chen and Yaguang Wang and Trakinin again. The front here is characteristic. In fact, they had to consider the solution in this anisotropic Sobolev space with half, roughly speaking, half normal regularity with respect to the tangential regularity. And because of the loss of regularity in the a priori estimate for the linearized equations, they proved the solution by a Nash-Moser iteration. Okay, we see that we can have, due to the presence of the magnetic field, some stabilization of the problem. Because in fact, if H is 0, okay, we get the compressible, from the compressible MHD equations and current vortex sheets, we get the compressible vortex sheets for the Euler equation. So it is the same problem as before in the isentropic case, say, with no magnetic field. So we have only the continuity equation, the equation for the momentum, and here the boundary conditions on the front, Rankine-Hugoniot conditions. Okay, so the so-called vortex sheets. Again, we may have a jump in the tangential velocity, so a concentration of vorticity. The linear spectral analysis says that in dimension 3, okay, the Lopatinsky condition is always violated, so we have the ill-postness, so-called Kelvin-Helmholtz instability. So you see the effect of the, let me go back here, they have proved the existence of solution, the stability for linearized and nonlinear problems. For the problem containing the magnetic field under these stability conditions, where H is necessary to get the well-posedness. If H is 0, you get in the 3D case the instability. Always, it is always unstable. In 2D, there is a bifurcation, say. So in 2D, there is a value of the Mach number. So if the jump of the tangential velocity is less than 2 square root of 2, the sound speed, again the problem is ill-posed. In the supersonic case, where this jump is larger than this quantity, we have weak stability. So in 2D, Kreis-Lopatinsky condition is never satisfied in the uniform form. But we can have a weak stability for Mach number sufficiently large. Okay, this is the problem that we had studied in a joint paper with Jean-François Coulombel, where we proved the existence for the second case of weak stability of the solution for the nonlinear problem. And the result, the linearized analysis, the analysis for the linearized problem was extended by Yaguang Wang and Fang Yu to rectilinear 2D current vortex sheets.
Why are the linearized equations stable for large speeds? Is this because the equation changes?
Yes, from elliptic to hyperbolic, essentially. This is the reason.
So it changes
Yes.
type and then it's stable because of that.
Yes, in one case you find the elliptic case, you find the growing modes, exponentially growing. And the other case, you get the weak stability, the hyperbolic problem. Weak stability means loss of derivatives in the a priori estimate, but it gives at least the solution, and it is hyperbolic. In the elliptic case, the problem is ill-posed.
Square root of 2, the magic number.
Yes.
Why is square root of 2?
There are discussions about the square root. But anyway, it is, you see, it is the correct number because less than, larger than, so it is that number.
So supersonic.
Supersonic Mach number or
Supersonic is stable.
Yeah, more stable.
supersonic is
Yeah,
more
banana
stable.
became more stable, yeah.
It is weakly stable.
Okay.
And by
okay.
the way, in the
Just to
limit,
remember.
in the,
It's just to remember before we forget.
okay,
Okay. So it's a cross. I mean, it's change of type.
yes,
Depends on the local analysis. You do something. If the type is elliptic, it works.
yes.
Okay.
But here, formally, if C of rho goes to infinity, which means that the Mach number goes to 0,
Yeah.
we have formally the incompressible limit. And in that case, if this one goes to infinity, this possibility disappears, and we get the incompressible Euler equations, which are always unstable, imposed also in dimension 2, as in the three-dimensional case. And for the incompressible case with the rotation solutions, one can write the Birkhoff-Roth equations and prove the solvability only in the analytic setting. Otherwise, okay, it is a long story. Okay.
Okay. Thank you.
Okay. This is the formal limit where the speed velocity goes to infinity, the Mach number goes to 0. We have the incompressible current vortex sheet, which is also interesting because here we have a precise description of the regions of weak stability or instability. Again, UKL is never satisfied, so it is always violated. And these two inequalities are necessary and sufficient for the weak stability. So if they are violated, the problem is ill-posed. If they are true, the problem is weakly well-posed. Okay. It can be shown that in this case one has the existence of nonlinear surface waves similar to the Rayleigh surface waves of elasticity. Okay, this is the region of weak stability. So in general, we expect a loss of derivatives in the energy estimate, but for the nonlinear problem, under these more restrictive conditions, so in a region which is a little bit smaller than this one, we can see that there is no loss of derivatives, which we hope will be useful for the proof of the existence for the nonlinear problem. And this is the last slide with Kelvin-Helmholtz instability on our planet and also on Saturn, in the atmosphere of Saturn.
So you mean that Saturn implies that you have magneto-electrodynamics, or just this different atmosphere?
Different atmosphere, probably. I don't know. I'm not an expert.
Do they have this charged atmosphere in these planets outside? Ionized atmosphere?
I don't know. Probably so. And also on the Earth, we have a magnetosphere, which is, by the way, described by current vortex sheets.
The standard analysis of these roles.
No. This is yes. We just use Euler equations or gravity waves and so on. Okay, thank you. This is.
Thank you.
Thank you very much.
More informal seminars.
Oh, yeah, I have a question. When you say that you don't lose derivatives in one of the cases, it is because, is there any explanation for playing people, for ignorant people like me?
Because
because usually you lose some derivatives, but in that case you don't lose them. So it's plain.
No.
It's what they call full
regularity. Full regularity means
Why?
there are different things. Full regularity for me means I can use standard subspaces. Otherwise, I have a loss of regularity in the normal direction, where each every normal derivatives is controlled more or less by two tangential derivatives. So I have half regularity, and I must use those anisotropic subspace with the asterisk. Okay, but it depends on the equation. It is not always true, because for the Euler equations with the usual no-slip boundary condition v dot n equals 0, non-slip boundary condition, the front, the boundary is characteristic, but for the Euler equation, which also has the vorticity equation inside in the structure, you can still use standard Sobolev spaces. So even if the boundary is characteristic, there is no loss of regularity.
Historical question. Kelvin and Helmholtz, did they ever meet and collaborate? Looks like they never saw each other.
Yes.
There was
Probably not.
I mean, they developed the theories completely in parallel.
Yeah.
Why? Because they
But more or less in the,
I'm just.
but more or less in the same period.
In the same period, but
Yes.
completely.
No, maybe they met. I don't know, but maybe they were not so far. But I don't think they collaborated. I don't know, but I don't
It's
think so.
parallel theory.
So your result is the same P result 2012. You say you can close non-loss derivative. Why is that under that condition?
For which
This is a linear estimate. They say you will not under a little strong condition. Then you say you can get energy estimate without the loss derivative.
but for which problem? I don't understand. In
Maybe
general.
The last one. Yeah.
The last one.
Yeah, 2012. Yeah,
This one.
Why this
Ah.
is because you use equation, you can tell us a little bit why.
Okay, the equations are
Because from equation,
here.
structure of equation,
Structure of the
under
equation.
better condition, use stronger condition.
Yes. By the way, no, sorry, I'm going the wrong
Yeah,
direction.
this one, this last.
Okay.
So you control normal derivative estimate under this condition.
See.
See?
Now, first I want to show you that.
Maybe you just will have us the key idea.
So H,
May I stop
H
here?
rod V,
You can
H
stop
rod
there.
V is the Lorentz